So welcome to problem 4-6. In this problem, we will play around with the convolution formula. The funny thing is, actually, this is one of the things that you guys have worked a lot with in the course Probability and Statistics from the beginning of first year. So this might actually be something that is just a piece of cake for you. Or if you, like me, cannot remember anything from former courses, then this will take a little bit of work to freshen up on. So what does convolution mean? Well, in general, if we have one stochastic variable that is distributed one way and another stochastic variable with distribution, for example, g, then we say that the distribution of x plus y, so the distribution of the sum of these two stochastic variables, is the convolution of f and g. So why don't we just say the sum? Well, that's because we say the sum of the two stochastic variables, whereas the distribution of the sum is what we call the convolution of f and g. Oh yes, and there is another assumption, just in the passing. Also assume that x and y are independent. That's actually quite important. So also assume that x and y are independent. Then we can use the convolution formula. So what is the convolution formula? The convolution formula for densities, so it can both be used for distribution functions or for density functions. So the version that works for densities is given as such. I think that the convolution formula tells us that if I want to find the density of y, in this case I have x1 that is gamma distributed and x2 that is gamma distributed with another set of parameters, then the distribution of their sum, so the distribution of y, is given as the integral over the entire real axis of the density of the first stochastic variable, x1, evaluated in y minus x. So evaluated in this y minus x, where I integrate with respect to x, and then multiplied inside the integral by the density of the other term of the sum, evaluated in x. Now note here that that sums are symmetrical, right? So I could have said y is equal to x1 plus x2, but I could also have said y is equal to x2 plus x1. So in any case, the convolution formula also gives us that the density of y can be written as the density of x2 evaluated in y minus x multiplied by the density of x1 evaluated in x integrated with respect to x. So right in this case, it doesn't really matter which one we choose to plug the y minus x inside, because x1 is gamma distributed, x2 is gamma distributed. The only difference is the first parameter. So their densities have more or less the same expression. However, sometimes if we're looking at the convolution of two distributions where the densities are different, like very, very different, then it might help to choose the right density to put the y minus x inside. So just remember that this order is not written in stone. Well, yeah, then I guess that was all there was to the exercise text, just apart from the fact that so the last point probably to make before we start calculations is to note that they actually give us the gamma density, and they say, whoa, be careful, remember that the gamma density is only defined for non-negative values. So remember that x1 and x2 have to be greater than equal to 0. And they remind us of that by giving us this indicator function here. And that is always a good idea to do when you're working with densities. Instead of just writing x1 greater than equal to 0, x2 greater than equal to 0 on the side, just put it all into the indicator function. And just in a while, in the solution, you will see why that is a smart idea.